Hi everybody. As we went through our lab test this week, I saw a lot of mistakes that teams were making to determine how the forces were really working in your scenario that you were given. A lot of assumptions were made that were partly correct, but because the relationship between two separate objects connected by a string and that force of tension in there, because there were errors made there, it made me worry about some of the bigger picture things. So we won't have class time to go over this, so this is the solution to think about your modified Atwood machine for the lab problem. So the whole idea, an Atwood machine is anytime we have two masses suspended over a pulley where they're able to freely move. A modified Atwood machine, you'll see that word if you Google search, if you look for other YouTube videos. Other people have better videos than mine that are worth watching, okay? So you've got your table, you've got a pulley on the end, you've got your block that had the weight sitting on top of it, attached to a string going over the edge to your hanging masses, right? So the reason this is considered a modified Atwood machine is that this object is not being moved by gravity on its side, only our hanging mass over here is experiencing any force of gravity. So there's going to be one direction that acceleration will happen in this type of situation. Many of you started correctly by determining that we have two different objects. I'm just going to call them object A and object B right now because I don't have values for any of them, that we need to draw a free body diagram for. So I've got object A. It is sitting on a table, so it is experiencing gravity acting downward. That's the force of gravity. We've got the normal force acting upwards. We've got the force of tension this way. And unlike many of the practice problems we've done, we're considering a real life example where the force of friction is acting in the opposite direction. So that's object A's free body diagram. Object B, we've got the force of gravity acting downward on this object, and we have the force of tension acting upward. Many of you wrote equations after this for net force for each separate object that were incorrect, or how you used them was incorrect because you just said force of tension cancels out. I want you to think about some real life applications here relating to strings and tension. This string here, what happens if you put 1,000 pounds hanging on it? Now, I don't just want you to say, well, it's going to go really, really fast because it's going to exert way more force right here. Let's imagine that I'm going to hold block A in place, and I am the Hulk. So 1,000 pounds, no big deal. So I'm applying 1,000 pounds of force over here on that little black thread. It's going to break, right? But if I only put a single paperclip hanging from this string, is it going to break the string? No. The force of tension does change depending on the mass that is hanging down here and the forces acting on the object up here. Tension is not just some constant value that cancels out. It changes depending on the forces acting on our other two objects. That's the whole reason we look at a free body diagram, because we're saying, no, these are two free objects. They are separate from each other. We have to mathematically show how they are connected. We cannot just say, I can obviously see, because they both have force of tension, how they interact with each other, okay? So for object A, we're going to look at this situation where our object is moving this way, around a corner, and this way. So I'm going to label a couple things positive and negative as I think about this. Since this is the direction of my acceleration, I'm going to call this direction positive. So that means anything that's happening either up or to the left in my system, I'm going to consider negative. So when I look at just object A, and I'm going to write the net force for object A, if this is the direction of my motion, I have two factors that I can consider in here, but I'm only going to think about my horizontal motion for right now. My net force, force of tension, is in the positive direction. So I have force of tension. My force of friction is acting in the negative direction. So that is my equation for the horizontal net forces for object A. For object B, I'm going to imagine I turn my paper sideways, that this is my applied force over here. This is still a horizontal direction if I turn it this way. So that's why I'm allowed to use those same directions. The force due to gravity is acting downward. And the force of tension is acting upward, which is my negative direction. So that is my equation for the net force for object B. If I want to find out what the acceleration of my system is, I need to solve for a force that both of these two objects are experiencing, which is going to be my force of tension, so that I can substitute those two values in for one another. I don't know how much tension is really on the string. Think about that question about, is the string going to break or not? Well, how many times are you surprised when something suddenly breaks that's attached by a string? We have to calculate and relate those other forces to determine what that force of tension is. So, if I want to find what's the acceleration of my entire system here, I'm going to find that by looking at that both of these objects here, object A is going to experience the same acceleration as object B. They both have different masses though, which is one of the challenges that we'll have to figure out. Since I have mass and acceleration, I'm going to substitute in my other representations for everything except force of tension here. And then I'm going to solve for force of tension for both of these. Actually, I'll do that in the reverse order. So, all right, let me start first. I'll do our object A, the box on the table first. So, I've got that the object A, its mass times acceleration, equal to force of tension minus force of friction. I'm solving for force of tension, so I'm going to add force of friction to both sides. And then I'm going to flip. What is that? Transitive property? You guys math better than I do. You'll tell me. So my force of tension, based on this equation, is equal to the mass of object A times the net acceleration plus the force of friction. So I have one equation there for the force of tension. I'm going to do the same thing now for object B. I'm going to solve for force of tension. All right, I've got mass of object B times that net acceleration. It's equal to the force of gravity minus the force of tension. Okay, well technically, because I hate negative signs, I'm going to do more than one step here. I'm going to add force of tension to both sides. So I've got MBA plus force of tension equals force of gravity. Whoop, move my page. Move it so you can actually see it. Sorry, I got stuck under my computer. And now I want to get rid of this mass of object B times acceleration from each side. So again, being laborious about my algebra, but that's so that I yield a second equation here for force of tension equals force of gravity minus mass of object B times the acceleration of the system. So I have two rearranged equations, right? Where did these come from? Up here, which came from my using Newton's second law for net force. And I determined these by looking at the horizontal direction, which becomes my vertical direction, based on my free body diagrams right here. So I'm going to flip to a new piece of paper, and I'm going to rewrite these two equations at the top. Okay? So I'm going to take those two equations and write them at the top of a new piece of paper. Okay. There's my new piece of paper. I now have two equations. Both are equal to the force of tension. Oops, not three equal signs. That's not defined as. mass of object A times A plus F. And then the other one is the force of tension right here. Fg must be. Okay. We get punchy the longer we work on stuff sometimes. So, what I'm going to do now is I want to set these two equations equal to each other. I now have a system of equations. One of the ways that we can solve a system of equations is by substitution. If this quantity equals force of tension, and this quantity equals force of tension, well, that means this quantity right here equals this quantity, right? That's the whole reality behind substitution. Before I do that, though, I've got several different quantities I'm trying to compare and eliminate to eventually find the acceleration, right? Eventually, I want to find this value for A. So I'm going to substitute in what is my force of friction right here, okay? So this line, force of tension, is equal to mass times the acceleration of the system, and force of friction is equal to the coefficient of friction times the normal force, right? Well, let's flesh out what does the normal force mean. It's going to be mass times gravity, right? And in this case, we're talking about the mass of object A. That's a little A underneath there. This equation for force of tension, force of gravity, is going to be mass of object B times gravity minus mass of object B times the acceleration. So I have two equations here that I have changed to only be in terms of acceleration and masses, which should make it easier for me to solve my systems of equation. So I'm going to take this equation right here and this equation right here and set them equal to each other. All right. Mass of object A times the acceleration of the system plus the coefficient of friction times the mass of object A times gravity is equal to the mass of object B times the acceleration of gravity minus the mass of object B times acceleration. Okay, now I'm just going to do a whole bunch of algebra and solve for A. So if it were me, I would fast forward through this part of the video. If I knew how to do that myself, I would. So I'm just going to mumble quietly to myself, and you should just increase the speed and listen to my mumbling, right? Okay, so I'm going to do this to both sides. I'm going to take this one and move it to the other side. So now I have this. A plus MBA equals MBG minus UMAG. Okay. So then I'm going to factor out A. I've got an A there and an A there. Just to make things pretty, I'm going to do the same thing on the other side. I've got a G, mu, M, A. And now I want to get A by itself, so. So, now, there we go. Sorry, that was off the screen, my bad. I've got, for my acceleration of our object, it's equal to the acceleration of gravity times mass of object B minus the coefficient of friction times the mass of object A over the sum of the masses of our system. That is the correct equation for the acceleration your objects are experiencing. Okay, I'm just going to fold this for a second so it's out of the way. But I want the green to show. What was the point of drawing it all pretty if I covered it up? So when we go back to your diagram here, and we're thinking about what is this acceleration A, it's this. It's this. So one of the questions you had to tackle in this lab challenge was, how quickly is this thing moving?